Okay, now it's time to introduce our next speaker, Tatsuya Sugioka. So Sugioka-san. Sugioka-san works at Sony, and Sony just had some very impressive earnings announcements last week and some good forecasts. So I was happy to see Sony really knocking it out of the park. And the biggest part of that is their image sensor roadmap and forecast. So that is exactly where Sugioka-san focuses. So I look forward to hearing you tell us about sensor formats, image sensor formats.
Yes. Okay, thank you for the introduction. My name is Tatsuya Sugioka from Sony. And today, I'm actually very pleased to be here and share my insights regarding the image sensor output formats and interfaces, especially for the IoT applications, which we are focusing right now for the embedded vision system. And I'm pretty open to discuss, so appreciate to have a lot of feedbacks or maybe even the requests from you guys. And okay. So today I would start to talk about the introduction of my company, Sony, regarding our image sensor business and technology evolution. And next, I'll a little bit deep dive into the explaining the image sensor output formats introduction and the what is the crucial formats for your embedded vision system. So, and lastly, I explain the interface choices for your embedded system. Now, we have a lot of choices, and I'll try to guide you to make a right choice for your embedded system. Like for referencing the some fundamental characteristic or performance of the interface, and also showing the landscape of interface specification or standard. Okay, this is a kind of introduction of my company. So Sony, we are actually been enjoying our successful history of the image sensor business and technology evolutions. We started, as you can see, back in 2008, introduced the back illuminated higher resolution, higher sensitivity image sensor to enable get a better picture quality. And then Sony introduced the stacked structure of the image sensor, which can enable the richer functional features in your system. Or basically, this is just showing the mobile market history. So, and then now, or last year, we introduced the dual camera for the smartphone market, or which might be seen booming in the market. I hope so. Driven by the giant company of the, smartphone maker, and which can enable the digital zooming, just like similar with the DSLR camera nowadays enable those kind of features, but with a bulky lens amount. So in this case, we don't need to have those bulky lenses. So that's I think good. And foreseeing the next step, maybe near future 2020 timeframe, we expect to have or enable the much more exciting features like 240 frame per second global shutter image sensor without any focal plane distortion, or maybe we can capture any scenes even in a very dark scene, night shot, or maybe crazy super slow motion movies or videos with around 1,000 frames per second. Get the email? So, but this is actually not today's topic. Kind of preface of my talk, and as you can see, this is a kind of linear evolution. So today, I believe we are here have a different motivation to be here to discuss. It says different from what we've seen in the mobile market. Now we are targeting IoT or embedded vision, so different dimensional evolution for maybe IoT sensors or devices. Last year, I think Japanese company acquired the ARM processor, and he said, CEO said, we'll see a kind of explosion of the IoT devices or sensors. So maybe IoT device will be composed of the sensor, of course, and some controllers for the edge computing or something. And also you will have artificial intelligence or deep learning CNN in the cloud side and connected through the internet. So we will see this kind of exponential leap of the sensor business Sony expects, and I expect my salary explosion. I don't know, maybe not. Anyway, so but the important point is, so we should leverage what we've done in the mobile market. You can see their established ecosystem. So we leverage those ecosystem and bring it to the IoT world to enable our future. So anyway, this is the last introduction. Sorry, so a little bit long. History of the image sensor architecture evolution. So I don't go to the details. Maybe it's boring. And the message here is integration in the image sensor. Image sensor will be much more a possibility to be more intelligent or integrated function, or as you can see, the massively parallel analog to digital converter can be implemented in the logic chip stacked behind the pixel chip. So, and also maybe extend the much more functions embedded in the sensors. That's a key message. We'll come back. So my talk today will cover two topics. One is output formats, and the second is interfaces. So first, let's go to the format. We have in the image sensor block diagram, it's a kind of example, but we have our image processing pipeline here, and that's composed the specific formats, standardized or something, okay. So image sensor formats enable various features, as you may know. Like for example, HDR, high dynamic range, and also electronic image stabilization, and ROI, region of interest. Actually, this is a kind of main hot topic for today, and the phase detection for autofocus. So let's briefly introduce those function or format. So the left-hand side is showing maybe the simple block diagram of your system, just connecting through those images like processor, image sensor, and gyro. Then you can enable those EIS or image stabilization. But on the other hand, we have an option to make your system simpler, like describing in the right-hand side picture. And your gyro can be connected to the image sensor, and the gyro data can be implemented or embedded between the frames, and just send it through the image, with the image. So this feature or additional formats can be used or beyond the EIS, and like we also able to embed the like temperature information or face detection or whatever you want, and those additional data can be embedded in the each between the frame and send it. So many more features enabled using. So this is a MIPI case example using data insertion by data type. Yeah. So next is HDR, high dynamic range example. We have a long and short exposure frame to make a higher dynamic range image. So maybe you know that this, in case of longer exposure, we have overexposure issues, problems. But in the case of short exposure, we have like noise in dark pictures. So we can combine them and get a perfect image. And those are features also enabled by this frame format, like combining long and short exposure frame using, in this case again, MIPI. They offer or provide the virtual channel features to differentiate those frames. So, and even they allowed to overlap them, then we can get the flexibility of the exposure time to manipulate each exposure time and get the perfect or higher dynamic range picture. So the next is a kind of main topic for today I would like to bring. So word of ROI or region of interest. Region of interest is a kind of common, maybe you know that, but it's a kind of crucial key function or format for IoT or embedded vision system. So the common or famous application is, of course, factory automation. They need to capture or inspect the products in the factory lines, and they also, our customer would like to have a higher throughput of the production line. So they need to increase, or I need to increase the frame rate, like 1,000 frames per second or whatever. But it's difficult to go through this with the whole image. So we should extract this specific region of interest area of image. And the another one is a wearable camera or police camera, body camera, whatever. So they also don't need to deliver whole image, but their interest is specific region, like license plate or criminal face, or those images should be delivered to the server and maybe processed. So, and similar case is surveillance. But in this case, we will have a bunch of region ROI, in this case Windows. Maybe this kind of intersection, a lot of people need to capture a lot of faces and send it to the server, and maybe CIA analyze these or those data, I don't know. Like, so, and automotive, which is a kind of hot region application, and vehicle to vehicle or vehicle to whatever case, of course, limited bandwidth. That's a problem. And also, we are heading to the autonomous vehicle, autonomous driving. Then we need to sense the with a higher rate or higher resolution, then the amount of data is much more increasing. That's problem. Impossible to deliver whole image, so we need to stick to the specific region or ROI. So the concept to deliver only the data you need when it's needed, so we can get a benefit from it, like reducing the power consumption or total system power, and maybe the different aspect, we can go to the enhancing your processor speed, or maybe reduce the latency of the processor, or of course solve the bandwidth limitation issue or save data storage. So let me try to explain a little bit details. It's kind of challenging part for me, but the total system performance improved. And so in this case, we are assuming two cases, like ROI done by in the sensor or your processor. Today we have a kind of ROI function in your processor, like post-processing, downscaling function. But the chart graph showing we have a benefit in case of smart sensor ROI case. So in the green bar, we can see a lot of reduction of the latency, total system latency. So this is a kind of calculation or estimation. So maybe it's good to show the demonstration better than my poor explanation. So the proof of concept demonstration composed by this kind of diagram and using the image sensor. And in this case, the ROI function or encode function will be implemented in the PC and through the low band channel, and another PC process the ROI decode and additional function like face detection. So, so my colleague, playing the, I don't know, soccer. Right? So this case, 3 ROI window, 2 faces and 1 ball, soccer ball, I don't know. And as you can see, it's simple. We can reduce the data rate or a bunch of data to be transmitted, and then we can increase a little bit frame rate. So we can deliver those data information even the very limited bandwidth channel. The next one is kind of difficult. So we have now enabled the face detection in the backend processor. Then, so we have a face detection feature in the backend side, and those features will be helped by the smart or sensor ROI. As I explained, your processor has a kind of ROI function like post-processing or downscaling. So those are processing latency or power can be reduced or can be alleviated and increase the performance of the system, or maybe in this case frame rate. So another point of benefit, automotive use case, it's not regarding the V2X, but in this case, long channel. Maybe you're familiar with the automotive interface challenging. Now we are a lot of proprietary interface, like, and also the standard of the Ethernet automotive, but it's limited bandwidth. So, and now we need to have like 50 meter or 40 meter length of channel for the case of autonomous vehicle, and of course the limited bandwidth. But again, and at the same time, we need to have a kind of wider range of recognition to avoid any collisions. So we need to detect any object far from you, like 50 meter or 200 meter far from you ahead. And for example, this is common kind of calculation to specify the image sensor requirements. 50 meter case, we need to have 2 megapixel, but in this case of 200 meter recognition, object recognition, then we need to have 8 megapixels. So that's almost impossible to achieve such maybe more than 5 gigabit per second data rate through the 50 meter or more, impossible. So, but we have our ROI, so we can increase the effective megapixel using smart ORI to extract the specific area of the region or interest of the region. So we can meet the customer requirement, like 200-meter range enabled. So those kind of ROI formats or features, actually standardization already initiated in MIPI Alliance. So as you can see in the picture from source from MIPI and like our ROI picture. So the important point I'd like to say, the common framework or common platform need to have, and that's accelerate our more efficient systems. And since we have a lot of sensors, a lot of type of sensors, maybe in near future soon, image and depth and IR. So those sensors can support the ROI function, but at the same time we need to your processor need to support the ROI. And you need to have common denominator to interoperate. Okay, so next topic. I need to go first in interface, output interface. So I don't go to the details, but as you may know, there are a lot of choices in even the interface for the image sensor output. There are a lot of proprietary interface as well, and even Sony we have a proprietary one. And of course we have a MIPI, and even MIPI they have a lot of choices. So it's making a lot of confusion. But I believe it's good to have this kind of menu. So we always good to have the menu. Just the point is pick up the best choice for your system or for you. So I try to guide you. So regarding the output driver, this is, I think, common, not new, but we have a history like LVDS and also going to the CML, current mode logic, to go first, but burning a lot of power. So another aspect or evolution should be done, like using sub-LVDS. I believe it's standard of the JEDEC. And this kind of output driver topology can gain the more efficiency of the power. So power is very important since we are talking about the image sensor. The image sensor quality, picture quality is degraded by the heat or power, so that's important. And another point is clocking scheme or system like source synchronous or embedded curve. It's maybe famous. Again, this is MIPI case. We have two type of scheme like D-Phi and C-Phi. And of course, embedded source synchronous, we need to have a dedicated clock lane, but embedded clock we don't need to have. And this is one of the example, but at least from the sensor perspective, not only for Sony, but the other sensor vendors saying, in this case, maybe C-Phi can reduce the power of the image sensor. So those kind of comparison or maybe investigation should be done to select proper choice. And next, of course, our target is IoT or embedded system. So basically, MIPI has been evolved in the mobile market, but now they're also focusing on the other beyond mobile area. And this is a kind of example of the automotive camera interface standards landscape, and the automotive Ethernet, but limited speed, around 1 gig, but the MIPI also now we have a MIPI in the automotive, but limited channel length. So the point is, of course, we are focusing or targeting sensing applications, so the long and much higher bandwidth kind of target should be standardized, those interfaces. So I don't have any conclusion for today, but maybe I'm working on it, and maybe next time more. So that we should focus on this kind of fight, which fight. In the case of MIPI alliance, but we have choices, and which fight will win for the IoT interface or sensor interface. So stay tuned. I don't go to details, but. So the conclusion is the key takeaways, and first one to more like formats, talk, insights, and more efficient embedded vision system can be realized via the evolving image sensor formats. And the key point today is dramatic extension of the range of imaging application in IoT world. It will be driven by emerging format like ROI. So, and lastly, the good choice, proper choice of the interface is important, and standardization is already been initiated to meet our customer requirement. So that's it. So, thank you very much.
Thank you, Sugioka-san. Do we have any questions from the audience? We have a few minutes.
Do you envision that the region of interest and like face detection will be done on the imager itself, or would the host do that from a previous frame? Is that going to be done real time on the image sensor or in the system?
Yeah, basically, I think we have a similar discussion in the MIPI Alliance too. Who will take a lot of pies of the the processing or your features. So now today, maybe processor has a lot of features or developed their features for the IoT or those vision features, but maybe the sensor will have a chance to be more smarter and integrated features than collaborate. I don't say take a whole pie, but just keep the balance and good shape to get the proper or better solution for the system and our customer. That's a kind of message. Is it okay?
Good. Does anyone have any other questions?
You mentioned that the ROI encoder-decoder pair, and can you explain a little bit more about the functionality of that encoder? Is it some image compression or?
Yeah, I know. So yeah, that's an important point. Data. Did you say compression?
Mm-hmm.
Yeah, compression. Right? Yeah, compression. So yeah, I forgot to say it's an important point. ROI function is more like similar with data compression, as you know. But for example, in the case of automotive Ethernet, they combine with the data compression like H.264. But that's as another problem like a latency issue, especially for the sensing applications. So, but I believe in case of ROI function, we can compress the data, amount of data, but also at the same time, we don't need to degrade this latency or the system latency. So that's a kind of interesting point to be investigated, and I'd like to discuss more, maybe, yeah, with.
Good. Oh, one more question? Okay, this will be the last question.
What about adding wireless for the interface? The high-speed 11AC, things like that coming? Replace wires altogether. Can you do that?
You mean to say wireless features embedded in the sensor, right?
Yeah.
That's impossible.
You have a
that's possible. Sorry, that's possible. Yeah, of course. most likely same way, like it's limited bandwidth, right? The problem is the limited bandwidth, or would
Right, that's, well, range and data rate, right? So, but the, these tethered AR headsets, they're looking at 11AC and other fast data rate, high data rate standards.
Yeah. So actually, I think there are some kind of proprietary solution. Some crazy ventures company provide like a wireless sensing device or image sensor wireless sensors. So, it's technically possible, and we, of course, Sony also investigated. And the problem is, of course, the power. Those wireless solutions, wireless technologies are basically or purely burning a lot of power, especially in the transmission or the power amp or whatever should be implemented. But maybe the differentiate the discrete chip incorporated in the board.
Maybe a companion chip.
Yeah,
Thank you.
That's possible.
Super. Thank you again. Thank you, Sugioka-san.